That's a very simple dependency, right? Rating determines W. What's wrong with it? You may wonder, okay, so far it's good. This is like a brain teaser problem we are having here. So what's the point? It's more than a brain teaser problem, okay? This goes back to the evil of redundancy in a database. Let me give you a specific example. Suppose that's your design, very naturally. You may find this design in many companies outside from the valley, right? Many small firms or company, even big organizations, they may have a table like this, very natural, right? I want to know for our employee, what's their rating and what's the hourly rate we should pay them and how many hours they have worked. Very natural. And together with their name and log information, right? But you know what? This is a bad design, unfortunately. Very bad. Why? Why this is a very bad design? Okay, let's look at this example. Suppose that's my design. Okay, now I give you a specific instance. Okay, I give you a specific instance. This design suffers from what we call the anomalies, from update anomaly, insertion anomaly to deletion anomaly. Actually, they are all the same. If you understand one, you should be able to understand the others as well. So let's look at, for example, update anomaly. Can we modify the wage value W in only the first couple of this instance? Yes or no? Well, in a database, if you don't have any constraint checking, yes, that's fine. You can go ahead and update that. But once you do that, what happens? You have violated this constraint. Meaning, suppose you update the wage value of the first tuple to $12, which means if you got a rating of 8, your hourly wage value is $12. But you do have another record in the database where this guy had the same rating value, but wage stay as $10. That obviously is not okay because now you have two records which have the same rating value, but values. Then the company might run into trouble. If the employee finds out, then we'll sue you, and you're going to pay a big fine if you have a good lawyer. Right? Yes, go ahead.
Would it still be considered an update anomaly, like a trigger of like any time that
So what you're saying is take them out to a separate table and make rating. Yes, that's a better fix.
Yeah.
Because yes, you can use both of these guys have excellent comments on this. Right? Let me repeat what they have said and make sure that the rest of the class can hear the proposal they have made. Right? Dylan said, I can use trigger. So that whenever you update the wage value associated with a particular rating value, I will go and make sure this update applies to all records with the same rating value. Meaning that when you update wage to 12, every single such association will be 12. But the problem with that is it's very expensive. If you have, let's say, 10,000 employees rating equal to 8, a single update like this will cost you 10,000 updates. And imagine if your database experiences a power failure in the process of doing that, you may end up with an inconsistent state. Some have been updated, some have not. Does it make sense? That's what we call update anomaly. What's your name?
Kincaid.
Sorry?
Kincaid.
Kincaid said, the better solution is to take this attribute out and put them into a separate table. Okay? Which I will, Dylan, let me show it, then I will let you comment on this. Okay? Which is like this. Why this is better? Because now if you want to change the wage value, go ahead, do it. Does it make sense? You only need to update in one place, and that fixes all the association between rating and wage, if they have the same rating value. Now, Dylan first, then. Yeah.
I guess I thought that wouldn't if like the thing with ending up in an inconsistent state, wouldn't that violate like with what SQL is supposed to say, it's supposed to provide like everything is supposed to be atomic.
So Dylan is jumping ahead. What Dylan is referring to is called ASIC property: atomicity, consistency, isolation, and durability. That's every single database system needs to ensure. And that's one of the reasons why database is so successful and widely used in practice. Here, I assume you're not using transaction. Later on, we will talk about transaction. Once you use transaction, it will ensure that even if database fails, it will recover to a consistent state, which is what the C means, consistency. We will talk about this later on in more detail. But here, I assume, since we haven't talked about this, I assume that you are not using transaction, then you may end up in inconsistent state like that. But the point is, even if you use transaction, with this design, it will be extremely expensive to recover from fault.
I'm going to ask, doesn't it have a log where it logs all of those and if it fails? It just
Yes, to ensure this, one of the many mechanisms database use to ensure this, one of them is to use log. And in particular, log itself is not good enough. Database system use something called WAR, write ahead logging, write ahead logging. This is jumping way ahead of what we're discussing now. We will discuss this when we come to that. Okay. All right. So yes.
Do these anomalies only occur when you have kind of an implied functional dependency? So, for instance, in that first table, the functional dependency was still rating to wage, but there was nothing specifically requiring that in the database. Whereas when you moved it out into another table, you kind of explicitly created that functional dependency. Does that make sense?
Kind of, but it's not really quote unquote implied, right? Functional dependency, like I said, come from you customers. Your customer pose those constraints to you.
Okay.
You as database administrator or designer, you do not determine that we have a function that R determine W. Your customer will tell you. If they enforce this, yes, you have to do it. But if they choose not, even if it's very intuitive to you, you do not enforce that because it's all depends on the customer application scenario. One last question before I move on. Go on.
Is the general idea that if we have a constraint that's not based on the primary key in the table, to make a table out of it?
Good question. So Natalie said, in generally the case, if you have a functional dependency, every functional dependency obviously will give you some constraint, right? Like a constraint tracking requirement. Even the case that every functional dependency other than the key functional dependency will imply that you want to decompose them into separate tables. I choose not to answer that right now. Keep that in mind, and we will talk about, this is the formally discussed under normalization, which is the topic after functional dependency, and we will revisit this always. Okay, all right, so that's update anomaly, but that's not enough, right? We may have insertion anomaly, which means if we try to insert another employee with a particular rating value, you cannot have an arbitrary wage value associated with that rating value. You have to check whether that rating value has already appeared in the database. If it does, the wage value of this new employee must be the same with whatever wage value that already exists for that rating. If it's a new, on the other hand, if it's a new rating value, you have the dilemma to choose what should be the right wage value for this rating value. That's bringing up the last topic, which is deletion anomaly. Let's say I delete the third and fourth employees. These names are really hard to pronounce. I need to change that to some simpler name to pronounce. Can you pronounce this name? Smash Thirst? Okay, anyway, these two guys, okay? Third and fourth guys. If we delete them, that's fine. Go ahead and delete them. But what's the problem? The problem is if you allow the deletion of those two records to take place, you lose something really valuable. You lose the information how much you should pay for rating 5. You lose that information forever. Does that make sense? And later on, if you choose to insert another employee with rating equal to 5, your boss comes like, oh, we have a new employee. He's rating 5. You ask your boss, how much should I pay him? Your boss might be upset with that, right? Shouldn't I told you this before already? Like how much to pay for each rating? Why you ask me this again and again? That's deletion anomaly, right? if you do this. So a way to fix this, as suggested earlier, which is to decompose them. Now if you delete these two guys, that's okay. You follow me? Why that's okay? Because this information is still available in the other table as long as you do not delete this record. In most companies, this is small, right? The number of ratings, possible rating value is small. So this is a fairly small table. Even if I have no employee at a particular rating value, I can still keep the rating and the wage association around without much overhead. Does that make sense? Rather than the earlier design where, because I want to know how much I pay for a particular rating, I need to keep just for that. Much. Now I'll give you a better. I said the reason we study function dependent normalization is to refine existing schemas, right? Let's look at. This is our good old friend, right? But now you should know this guy really, really well, right? Like they're your friends. Look at this picture. So I have. Let's say I have a attribute called lot associated with employees. Like I said, that determines where you immediately. I need to add one more attribute to the employee entity, which means employee table, because every entity. So the first diagram, the corresponding table becomes, we have a one, by the way, we also have a one-to-many mapping between department, meaning one department have multiple employees working in that department, but each employee works in only one department. And you do not produce a table for that one-to-many relationship set. One side and place that into the many side. So you have two tables. One is called workers, social security number, name, lot, department ID, and the attribute for that relationship set, which is the date, since when this employee worked for that department. So I have 5 attributes, S, N, L, D, to distinguish things, and as I said, I use SI for that date attribute. So far so good, right? And department entity set goes to a table by itself, which has DID, DName, and budget. So I use D for DID, M for DName, and B for budget. Everything looks fine, right? So far so good. Now one day, after you have this one day, the boss came back and tell you, okay, we have something new, which is it used to be everyone can park in any lot he or she liked. And that created a lot of chaos to the company. The company decided to do the following, which is we're going to assign a fixed lot for each department. Do all of you follow me? If you work in the same department, you go to the same lot. That totally makes sense, right? A lot of companies do that. Now, with the discussion on functional dependency, you should know what that implies. That implies a functional dependency, which is, what's the functional dependency imply? D determines lot. If you have the same department ID value, the lot value must be the same. But remember, functional dependency says if the department ID value are the same, lot must be the same. What happens if you work in 2 different departments? It doesn't say anything about that. It's possible 2 or multiple departments are assigned to the same lot. That's what will be the case, right? Because the size of each department might be different. The engineering department might be much bigger than the marketing department and the sales department. So the marketing and sales department is assigned a single lot. Engineering department has a single lot. In reality, it's oftentimes it's the other way around, right? You have more sales and marketing people than engineering people. Why? Because these guys need to sell something $10 to $100, right? So they need more traffic. You have more people over there. But let's say the distribution of the workforce to different departments is different. So multiple departments could be assigned to the same lot, but that doesn't violate the functional dependency. If DID value are different, I don't know whether they are in the same lot or not. I didn't say anything about that. If the department ID value is the same, then lot is the same. Okay? What's the problem with this approach? Can someone tell me? Once the design you have on top is fine until this point. But after I know you have this dependency, that design on top is no longer a good design, suddenly become a bad design. Can someone tell me why that becomes a bad design? Huh? I want to ask somebody else. Hey.
Because you can have more than one lot, and each employee can have more than one
No,
lot.
each employee, if you think about each employee has the same department ID value, because he or she can only work for one department, which means he or she can only have one lot. But what's the problem?
Making sure that the employees park in the right lot is difficult.
Make sure the employee park at the same lot become difficult. Actually not, because both department ID value and the lot value for that employee are from the same table. It's a simple constraint checking you can do, enforcing over that. But you're kind of right, meaning that this approach will have more overhead because you may have repetition of that. Yes?
You could redundantly store the same lot for many different departments, and then updating that would be the pain, I guess.
You have redundancy, that's the key word. You have redundancy in the workers table where the department ID value and the lot value association may be stored multiple times. Does that make sense? It's the same problem as rating determined wage. Imagine in the workers table, I have 1,000 employees from a particular department. They have the same DID value. What's the problem? You will store the same lot value for those 1,000 same DID value how many times? 1,000 times. And that suffers from insertion, deletion, and update anomaly we talked about in the earlier slide. You follow me? Yes or no? I hope you do, okay? So how do we fix this? Well, you fix this using exactly the same trick as we did here, which is make a new table and remove the lot value from the employee table, from the worker table, and then create a separate table for the department and lot association, such that even if I have 1,000 employees work for the same department, I do not have to store the department ID and lot association 1,000 times here. I only need to store that once for all those 1,000 employees in a separate table. Do you follow me? Now, if you go one step further, you realize instead of having 3 tables like this, a better design is to go back all the way to your ER and move that lot attribute from the employee entity set to the department. You end up with a design like this. The department lot is the same. And in fact, that function, once you move lot here, this functional dependency is automatically enforced by the key constraint on this table, because DID is the key for this table. You don't even have to introduce additional constraint to enforce this. So that's a better design. But this is a better design only after you know this. If you do not have this, if your boss never tells you this becomes a bad design. So bad, it doesn't even work. If any employee tries to park anywhere he or she likes, then this design doesn't even work. Does that make sense? Yes or no? I hope I'm making sense here. I see you guys need to give me feedback, right? Either it doesn't make sense or it does. If you're puzzled, that means it doesn't make sense. Okay. All right. Question.
So is it okay to say like a
Louder, please.
Is it okay to say like a functional dependency is like adding a one-to-many relation to your?
Not really. No, no, no. It's not to add one-to-many. Functional dependency is to add more constraints to your design, but it's not necessarily one-to-many constraints. Okay. All right. So this shows you the power of functional dependency, right? Using a simple concept like this, you can actually go back and refine your design all the way to the ER. That's what I talked about, right? Earlier. You already have a database, you want to refine its design. That being said, now I'm going to talk about something interesting, right? Reasoning about functional dependency. This is like some really interesting discussions, right? So given some functional dependencies, we can usually infer a determine the studio and the star. Meaning, given the same movie title, they must be from the same studio and produced by the same stars, featuring the same star. So this writes to title determines studio and star. This actually implies both title determines studio and title determines star. What that means? Okay, I'll give you another example right here. If I have a design like this, this is a very natural, very intuitive functional dependency, right? Student ID determine age and name. That's a key that obviously determines everything from the student schema, so this is totally fine. This implies and, right? This is very simple. But I ask you why. It's actually not that trivial. Why this is the case, right? I will give you the formal proof for this. Yeah, I will give you the formal proof for this. How do I prove this? I will show the proof right here. Can you see, or should I turn on the light? This is good, okay? All right. So the proof, how to prove this? Okay, this seems like very natural inference, right? But simple things like this, you still need to prove this. How do you prove this? In general, what you need to prove is, if you have A determine BC with respect to a schema R, then of course, both with respect to still the same schema R. That's what we need to prove, right? Do you follow me? So how do we prove this? We prove this by definition. The definition of functional dependency for any instance R from capital R and any two records T1, T2 from small r, given A determines BC, what do we have? We have if that's the case, then we must have you follow me? Yes or no? I'm not doing any trick. All I'm doing is by the definition of the functional dependency. That's all I'm doing here. And I call this fact number 1. Do you follow me? That means, now is my induction. That means for any R from schema R and any T1, T2 from R, if projection A equal to T1, projection on A from T1 equals projection of A of T2, then projection of B of T1 must equal to projection of B of T2. Why? Because B, C value are the same, implies B value must be the same. And for the same argument, C value must be the same as well. Both of these are using this fact number 1. Does that make sense? And this basically give you A determine B. This means A determine C, both by definition and no proof. Okay? Do you follow the logic of this proof? I basically prove this using definition, nothing else. Using definition of functional dependency, A determine BC means A determine B and A determine C. When A value are the same, B and C value are the same for any record. So when A value are the same, B value must be the same and C value must be the same, independently for any record. That's essentially what the proof says. You follow me? And the next one is interesting. If title determines studio and title determines star, they imply title determines studio and star. Meaning not only you can break them, you can combine them back as well. This is also very intuitive. I'm not going to go through the proof, but the proof is similar. For any two records, if title value are the same, we have studio value are the same based on the first function dependency, and star value are the same based on the second function dependency. Hence, as a result of that, if title value are the same, the combination of studio and star value must be the same, because both of them independently are the same. So when you put them together, they are still the same, by definition. That means title determines studio and star. The last one is what we call transitivity. If title determines studio and studio determines star, that implies title determines star. This actually requires some more effort in terms of the proof. Let me quickly summarize the proof. For any two records of view choice from any valid instance, if the value on the title attribute are the same, the first functional dependency tells you the studio value must be the same, by definition of functional dependency. And the second functional dependency at the same time tells you for any two such records, so that the first two random choice you have chosen, this condition will apply to those as well, because any two records. So these two records you have chosen must be part of it. If the studio value are the same, star value are the same. Combining these two facts, for any two records, title value are the same means studio value are the same. Studio value are the same means star value are the same. So automatically I have, for any two records, title value are the same means the star value must be the same. That's the definition of functional dependency. And no proof. Okay? And in summary, we have these three rules called reflexivity, augmentation, and transitivity. X determine Y means if X is a superset, I will overrun for like 1 minute. Okay? If X is a superset of Y, schema-wise, right, in terms of the attributes they have, then X determines Y. This is easy to understand because if X value are the same, since Y is part of X, any part of X must be the same, so Y must be the same. If X determines Y, then X determines XZ and YZ. XZ determines YZ for any Z value. Meaning you can augment an existing function dependency with the same attribute on both ends. I will formally prove this next lecture. Transitivity, which is what I have gone over just now. If X determines Y, Y determines Z, then X determines Z. Keep this in mind. Unfortunately, we have a long break before we come back and revisit this topic because we have midterm on Wednesday, then spring break in between. Make sure you make good use of the spring to work on the project and to keep your mind fresh for this so that I don't have to repeat myself when you come back. Okay?